If you haven't already, please check out my previous video where I show you how to use this equals average weighted function to find the weighted mean. Now I'm going to be using that function to find the average outcome or expected value for discrete probability distributions. This is essentially the average number that we would expect over the long run if we average, add up, and divide all the outcomes that we get. It's great for things like games of chance. If you want to know if you played a game again and again and again, would you on average lose money with a negative profit or make money with a positive profit? Of course, you do need to know probabilities for those outcomes. We can also use this for insurance policies if we have a known probability roughly, and we'll look at a problem like that as an insurance company. Let's start out with a problem where we're selling an insurance policy for $500. For most people, they're not cashing in on that policy. That's revenue with no costs. Maybe we already factor in some operating costs. That's too complicated. We're going to look at a simple version. So just $500 revenue without any payout would be pure profit. We'll wait on the weights a second. Let's look at the second outcome, which would be someone who cashes in on that policy. So we already made the $500 revenue by selling the policy, but now we need to pay out. Let's say we pay out $50,000. Then that is a loss of $49,500. Let's start with the probability of a payout first. Let's say we're only paying out 0.75% of the time. That's 0.0075 as a proportion. Then that means the rest of the time, or 1 minus 0.0075, is 99.25% of the time we will make money. And here we see that on average, if we sold these policies again and again and again over the long run, as the insurance company, we would make $125 profit based on these circumstances. Now, if I was the person buying the policy, everything would be flipped around. My profit would be negative when I don't use the policy and positive when I do cash in, even though it's kind of doesn't make sense because I'm not in a great situation there. But here we can see that on average, people are losing money on these policies. And that is kind of part of the risk of this thing is you're expecting that, some of your money is just going to this company's fees and operating expenses. But it is risk and kind of planning ahead for those negative situations. Now you could use this for all kinds of different expected value problems. Here I've got a set of discrete outcomes and probabilities that I could paste here and show an expected value of 2.47, just multiplying together the outcome times the weight and adding them up. Now there wouldn't be any dividing because I would divide by the total weight, which would be 1. And that kind of brings me to my formulas. I've got this Libra textbook open here to show a couple formulas. First, the mean or expected value is the sum of x times p of x. So it's the same way we would do the weighted mean. I'm going to do that by hand now though. So I'm going to create a column in my spreadsheet for x times p of x. And I'll create another one that I'll use in a minute for my standard deviation. And there's a couple different ways to find it. One of them involves subtracting the average from each outcome. In other words, how far is each outcome away? And it ends up being a little bit more procedural. It's actually easier if I use the second version. And I'll need that column. Anytime I see the sum, it means adding up all the rows of a column. So whenever I see that big sigma, I create a column. This one's going to be x squared times p of x. I'll come back to those formulas in a minute to build these resulting formulas, but for now, I just want to get what my row results would be. The first one is equals x times, I'll use shift 8 and p of x. So that's equals a2 times b2 for that first row of data. Once I hit enter, it's got this great autofill, which I'll accept. And now I'll repeat that again for column D. This one is x squared times p of x. So for x, I'm going back to column a2 squared times b2, and again, autofill. So I've got my x times p of x and then x squared times p of x columns. Suppose later I have data that go a little bit farther down into this spreadsheet. For example, here I'll type in this data set, and I'll need to know how much probability is remaining there. That's actually 0.24 remaining. And a total probability of 1 or 100% now, just to make sure that I meet the requirements of discrete probability distributions. And we see that the formulas don't come down far enough. So each of these can be filled one at a time, or you can even fill both of them together. Highlight whichever cells you want to fill, go to the bottom right corner and click on that big dot. And if you just drag it, you'll be able to fill down, or you can double click and sometimes it will snap it all the way to the bottom if you have 100 rows and it's a little bit tougher to drag. Now I've got all the information I need to calculate both the expected value, which is the mean, and the standard deviation. I'll just type standard dev to fit that in. The expected value is the sum of x times p of x. This function will be really easy for us, just equals sum, and then an input is column C. We'll use the whole entire column there. And that gave me an expected value of 3.2. This suggested fill I don't think is going to be what I want. I don't know what it's trying to do there. But I can double check and make sure. Copying and pasting this back to the average weighted, I've got that 3.2 there. And now for standard deviation, I need a square root, and then I'll add up that column I made with the x squared times p of x, and then I'll subtract the mean squared. So equals sqrt to bring up a square root function. Then I had the sum of my x squared times p of x column. And then I have closing that sum and subtracting the mean squared. That would be g1 squared. So I did move over so it looks kind of weird. You can see my function in a couple places at the formula bar or down in that cell. But that is the square root of the difference. And that's telling me that inside the square root is a subtraction problem. And it's the difference between the sum of column D and the expected value squared, or mean squared. That one is tricky to find. A lot of times I'll use staplet.com to find these, but it is good practice of using some basic functions and formulas in spreadsheets to find these. What we also learn is how much we expect to deviate from the mean. 1.5 in either direction is the standard deviation. And that information is great for distributions that are spread out over a wide range of values.